Hello, Dr. Crawford. This is Bruno, and I'm going to do the presentation about my final product on the remote sensing class. And my project is about the estimation of the flood's impact on agriculture and land use using remote sensing in the state of Rio Grande do Sul in Brazil. Well, the first flood that it was studied on this project was the flood occurred in 2023 on September. And on this flood, it was a huge disaster for the state of Brazil. And there was around 200 to 300 millimeters above the historical average of rainfall. Over 100 cities were affected, and the rainfall totals reached almost 700 millimeters, the second highest recorded in 100 years. And the first one was the one in 1941 with 400 millimeters, and it was another flood caused by rainfall. And this flood destroyed over 50% of cities like Mussum, the one in the picture. The second flood that is studied on this study was the flood of May 2024 of this year that I was there during this flood in the city of Porto Alegre, the capital of Rio Grande do Sul, and it was the most severe flooding event on record for the state, affected almost 500 cities. So it was basically all over the state, and the rainfall reached a total of 800 millimeters in many places, and this was above almost 300% above the expected for the region. Well, my area of study was here on the state of Rio Grande do Sul. This is the southwest state in Brazil, and my region of study was here, uh, between the city of Caxias do Sul, that is the one above here, and another city down here. And I've tried to focus on this bridge, which is the one bridge that fell during the disaster. And this is an image of the bridging being exploded after the disaster, so it could be uh, constructed, built again. And we can see that the bridge, one of the pillars succumbed, felt because of the water pressure. So the road was already like this, falling. So no access was possible after the flood. And this happened to many bridges in the south of Brazil. And I chose this area because the pressure of the water was really great, really intense in this region, and there's a lot of agriculture and forest areas around it, so it's probably good to study. Well, the methodology that I use it based on my literature review, uh, I'm going to try to illustrate it here. I took the data from Landsat 8, C2 and L2 level, and the study area was around the Cai River, Cai in Portuguese, and I took 4 images. The initial plan was to take 7, but due to cloud cover and another reasons, I just took 4. So one before the two floods, one of the flood in September 2023, another one from May 2024, and one after the two floods on September 2024. After all of this, I did the layer stacking with all the necessary bands, and after that I clipped the the region of interest on Erda's imaging, and I got pictures, images like this. This is false color, of course, and this is a picture of the whole area uh, that was downloaded from USDA or from the Earth Explorer. Well, after I clipped the region of interest, I applied this indice which is for flood and water extraction. It's a novel indice that I found out on Google Scholar, and I thought it was really interesting for this project. It uses these two equations. They are very basic, and the first one is to calculate this MT, which is the division. First, I need to sum blue, red, and green, uh, um, and divide it by 3, getting a mean of these 3 values. So you can get like you can have less impact of these 3 bands and get a better understanding of the dimension of the flow. And after that, you need to subtract from the near band. This formula it was for Sentinel, but I just converted for the Landsat, which would be band 5 here. And after calculating this, I got images like this one in the center. The area around was from the raw data, just after I clipped the region. So after that, I did a unsupervised classification, and I got 3 classes: forest, agriculture, and water. Forest is the dark green, agriculture is the bright one, and water is the blue on this picture. And I use it a specific kind of unsupervised classification, trying to get the better of it. I try like many times to see which one would fit better my interest of getting the water corpses, and this one was the better, using minimum 4 classes, maximum 6, max of 15 iterations, and these others pattern. After that, well, I mean, that was already a result, but another result was through the binary transformation that I did on QGIS. And a few things I couldn't do on Nerdus. I tried, but it was really hard to find out how to do it. So I just did it on QGIS because there's more videos and classes about it on YouTube, and there's more research too on the Google Scholar. So I used the raster calculator, and water received the value 1 and the other categories value 0. And the formula was basically subtracting one image from the other. And I got in first place this one, which was the binary transformation. And after subtracting, I got pictures like this to know like the movement of water between one year to the other, and, and things like this. Well, talking about the results in Scotian, uh, in these results we can see the evolution of the river course in this region, and this picture is before the event, so we can see the probably normal course of the river in the normal dimension. And in this one, we already can see a misclassification on this picture, because uh, these two features, blue, were actually shadows from this mountain that is here. So it was a misclassification. And this picture, it was from the first flood. Then we already can see an extent of the water feature. And this was the biggest flood, and you can see a lot of render areas with water, and the dimension of the river is really bigger. And this is a picture after all the floods, where you can see that the normal size of the river actually was increased after the two floods, and probably it did not uh, went back to its original dimension, uh, because it was actually a short time after the flood. It was still the same year, so probably if I took another picture later on, maybe the river course would be smaller, which would be something interesting to do in the next analysis. This one is just this kind of the same picture, just focusing on the water, and I did this one with the binary transformation, just putting all the other values like 0, so I can get like all of them, all of the other categories in dark. and I could see better the water extent on this one. And this was the difference between two dates. And on this first one, on the A picture, is the difference between the biggest float and the picture before the two floats. We can see that there's many areas that it's not even the river, but it's categorized as water, probably because it was really flooded because of the rainfall. That that is actually normal. In my state in Brazil, a lot of areas that was not in contact with river was flooded too. So I think it's normal for the region. And we can see that there's a huge difference between the the normal distribution of the river and after the flow. And this is another picture that I thought that was interesting to put in the presentation and in the report, which is the difference between before and after the float. So you can see there is already a difference between the two, uh, because probably we would expect to the river go already to its original dimension. And this is another result, this time with the classes of agriculture in bright green and forest on the dark green. And we can see that there's already uh, some difference between the pictures, which are interesting. Like in this region, we can see there's not so much forest and in these three first ones, but in the last one, there is already a lot of forest here. But this is probably due to misclassification. As I showed on the report, there was a increase of around 10% of forest dimension. So it's probably misclassification because I don't think, and this is like 100 hectares, so I don't think it was planted. And I think it's just a misclassification, which is the same for this blue area, which is actually the shadow of the mountain. And but we can see that there's a reduction uh, on this last picture on the agriculture dimension and category because of the rainfall, probably because a lot of soil was lost to the river by erosion. So a lot of areas would probably be abandoned or needed to go through some management to go back to its original states. This is a graph showing the change in area of land classes over time, and we can see that in the beginning, before the floods, uh, the area of water was smaller when comparing with the final, and there is a huge um, increase on these two dates, categorizing illustrating the flood impact. And another thing that I already talked about, we just can see maybe better here, is that the agriculture category had a decrease when comparing with the beginning, before the floods, and the forest area has had an increase between the two of them. And another interesting thing is that just in the last date, the forest and the agriculture area had like the biggest changes. Maybe that's because of misclassification, or maybe because it's really like that, and maybe further analysis is needed. Well, the conclusions about this project, I divided it in four. The first one is about the impact of the flooding. Well, the flooding causes significant disruptions with an increase of 88% and the area covered when comparing before the flood and after the biggest flood. And this resulted in a loss of 15% of agricultural land and underscoring the vulnerability of farming in areas so close to the river, which are not recommended in Brazil. But before the law of this was implemented, there was a lot of areas like this in Brazil, mainly cultivating like rice and sometimes even soybean and corn. And the second flood was the most profound impact, but uh, this reflected the intensified nature of the extreme event and intensifies the need for do research like this so we can prepare better for next floods. When talking about the methodology, the integration of FWAI and supervised classification provided a quantifiable and scalable results, actually capturing change in land cover and flow dynamics. And I believe that this methodology is suitable for application in other flood-prone regions, supporting disaster and this and making it better for preparing for other disasters. But I believe would be better to get hyperspectral data instead of multispectral, as I did. But it was not available. I tried to find, but it was really hard. And maybe working with LiDAR, which was actually the my first idea, but I couldn't find. I asked professors from the university, and I couldn't find a source of this, which would be good, like to do measurements like calculating the loss of soil in the profile, which I was really interesting, but I couldn't find the data to do it. Another conclusions are the challenge and recommendations. There was some misclassification as I talked about, and like the 10% increase in forest areas that I don't believe it was true. So maybe there's uh, probably a way to improve this kind of methodology. And another conclusion would be about the significance of the disaster management that actually I already talking about. So it's good to keep this studying so we can prepare ourselves better for the next floods, which had so much impact on the south of Brazil, uh, because a lot of people actually lost their lives and houses and much things. So I think this is a really important project and kind of study. Thank you very much, and thank you for all of the learnings from this semester. I think I learned quite a lot. And well, thank you very much, Dr. Crawford.